Weight and mass. Ooh, ominous. That came out of nowhere in the video. My apologies. So this is, we're going to do two systems of measurement. And in the English units, we start with pounds, which get abbreviated like pounds. Now, if you're actually in England, they would also have stones, which stones didn't come over here. I'm trying to remember, I think stone is like 14 pound. I used to live in England, and the doctors would talk to you about how many stone you weighed. Now, weight has to do, if we have an object in a gravitational field, the gravity pulls it down, and it generates a force. And that force is the mass of the object times the acceleration due to gravity. On the surface of the Earth, the acceleration due to gravity almost everywhere is the same. So early measurements of weight people thought was an object's mass, because they didn't see the effect of gravity everywhere. Mass is a measure of how much stuff, how many atoms, how many particles make up an object. And the mass won't change. If I were to take, a bowling ball, and it would have a weight on Earth, a weight, which is the mass times acceleration, and I'd take it to the moon, it would weigh differently because the mass times the acceleration on the moon would be less, but its mass would stay the same. Now what happens is, in the metric units, we measure mass in grams, kilograms, and weight in newtons. But in the English system, we're going to talk about weight in pounds. And what tends to happen is we convert between the two as if they're the same. We just acknowledge that we're doing it on the surface of the Earth. And so these conversions are, they're not scientifically correct, but we are using this underlying assumption that all this is done near the surface of the Earth. And so in our English system, we have 16 ounces is equal to 1 pound. And we have 2,000 pounds is equal to 1 ton. And those are our big weight conversion factors in the English system. In the metric system, we have a kilogram, which is usually actually the base that we use. Kilogram is a fairly, it's less than a pound, but a kilogram is a fairly nice unit. Though when you're working with medicines, we might even go down to milligrams. And so in the metric system, let's see, we have the gram as the base, and then we're going to have a decagram, which we'll abbreviate as decagram, and that is 10 to the second, 10 to the first, sorry, grams. Then we're going to have a hectogram, which is 10 to the second grams. And then a kilogram, which is 10 to the third grams. And then we can also go downwards. We have a decigram, oops, decigram, which is dg, which is 10 to the negative 1 gram, a centigram, 10 to the negative 2. Notice these prefixes get the same name. Doesn't matter if we're doing length or anything. Centi is 10 to the negative 2, deci is 10 to the negative 1, deca is 10 to the first, hecto is 10 to the second, kilo is 10 to the third. Always, no matter what the base unit is. It's the other good thing. And milligram. And I think milligram's the one that we're probably used to hearing because that's within our drug dosages. And medicinal doses, we tend to talk about things in milligrams. So, again, they used water as the linking thing. So 1 kilogram of water is equal to 1 liter. So so notice how volume goes back to shape, right? 1 centimeter cubed was 1 milliliter, and they linked that also to the volume of water. And they used water as the linking unit here. And so there's some nice linkage. And the reason they did that is water is common on Earth, common in the things that we use. And so by doing this, they were able to create a system that was very easy to do conversions within measurement. So let's kind of go back and think about our aquarium, right? So if an aquarium holds 0.25 meters cubed of water. So I measure out my aquarium and I do my volume equals length times width times height, and I get something in centimeters cubed, and I convert it to meters cubed, right? That's where we're going with this. Well, what we want to do is we want to turn that into how much is that going to weigh? And so what I want to do is take 1 liter and convert it to volume, and then convert 1 volume to kilometers. So what I remember that a centimeter cubed was a milliliter. So I'm going to use that. Now there's other conversion factors in the book. We make our conversion factors, but I'm going to use the fact that I remembered that 1 centimeter cubed was equal to 1 milliliter. And I'm going to use this to figure out how much does this water weigh. And I know 1 kilogram is 1 liter. So that's going to be the chain I'm going to go through here. So I need centimeters upstairs and I need meters downstairs. And I know that this is 10 to the negative 2. And so I'm going to cube that. Then in, right, because now I have meters cubed will give me centimeters cubed. And my conversion's down here. Okay, because 1 centimeter is 10 to the negative 2 meters. Any one of these equalities I can turn into my conversion factor. So now I have centimeters cubed. And so now I'm going to do this. 1 centimeter cubed is 1 milliliter. And I'm going to multiply. I'm going to turn this into my fraction 1 here. And now I know that 1 milliliter is 10 to the negative 3 liters. And I know that 1 liter is 1 kilogram. And so I look at my units. Centimeters cubed, meters cubed. The meters cubed is canceled. I'm in centimeters cubed. Centimeters cubed cancel. So now I'm in milliliters. Milliliters cancels, I'm in liters. Liters cancel, I'm in kilograms. So this will get me what I want as conversion factors. And what I need to do here now is I need to across. So let's see here. 0.25, and the meters cancel here. And so, well, what is 10 to the negative 2? That's 10 to the negative 6th, but that can come upstairs as 10 to the 6th, right? And then I'm going to have 10 to the negative 3 here, using my exponent rules, right? Cubing something is the same as multiplying by the power. Negative powers come upstairs. And so everything else is factors of 1. And so using my exponent rules again, and my units will be kilograms in the end, I get 0.25 times 10 to the third, or this is kilograms, or 2.5 times 10 to the second kilograms, which is 250 kilograms. The metric system is set up to do these quickly. Most will have powers of 10, so all you need to do is focus on the exponents. Practice the problems and practice doing them like this, especially if you're looking at doing anything around medicine, because certain fields like nursing require you to do your dosage calculations in your head. That's to make sure that you never make dosage mistakes and you don't rely on the tech for it. I remember having a friend as a nurse during Tropical Storm Sandy, and the power had been out for days in Jersey, and so they had no tech, no phone, and they're used to doing these things in their head. And it's still a requirement in a lot of nursing programs to do your conversions, your dosage calculations in your head. So if you practice now, getting used to lining up these conversion factors, they'll work for you, and you'll find that the metric system, a lot of things, look how many ones were in here. And there's a lot of ones that go away. And so when people talk about why is the metric used for science, this is it, right here. It makes converting and doing huge problems like this. I mean, this is a huge problem. If I were to give this to you in the English system, it's too much work. You need paper, and you need to, or here, you can start holding out pieces of it in your hand. And that was the purpose. All right, we're going to move on, and we're going to look at some geometries now that we can measure things. We're going to look at some particular geometries.